And today I will do it a little bit differently than before, because I wanted to show the paper and a little bit of an outlook before we take the break. Wait, I will do it like this. Okay. So today I will discuss a little bit about this paper by Bravyi and Gosset. It's a very long paper, so I will allow myself to just skip through the entire paper and just show the technical formulas that we will be interested in. So, and this will also show what kind of stuff we covered and what kind of stuff we still want to discuss. So the notation will be a little bit different than I was using it. So for example, here we will have x being the mu strings that we usually considered. So my notation was 0, 1 until, for example, 2L. And L was, for example, the length of the chain that I was considering. C of x is what I was writing as mu, m of mu. So it's like a Majorana monomial. And then this is very similar then to what we were writing. So for example, an operator A hat would be expanded as a mu m of mu in the Majorana basis. So this is basically taken from those kind of papers by Bravyi. I think he had some earlier papers than this where he was using a similar notation, but this should all look familiar. Then I was writing omega g of an operator A. So here it's different because it's the argument here is kind of indicating which kind of Grassmann numbers we will be taking. Here the Grassmann numbers are taken to be theta. I was taking G for Grassmann numbers and then M for Majorana operators. And yeah, and then F I have for fermionic operators usually. Anyway, Grassmann algebra we were writing down, and this was G of mu, which we had as a monomial as well. Then I was introducing the notation integrating against a Grassmann number. So that would mean that I have G2L ... until G1. And that's basically this integral that we were discussing, which means that that in our notation, G of mu is Kronecker delta mu with 1, and I think I was also using a bar for the fully one string, just as here. So that was one integral that we were discussing. And then here already we have something going towards Gaussian stuff. So in the notation of previous recordings, it would be something like this, just a quadratic form. I'm using A and B usually for indices. Here P and Q are the indices. Normally I would probably use P and Q also as Grassmann numbers. Okay, so so that's basically the overview of the notation that we will be looking at. Cannot scroll like this. Okay, so I scroll down a bit more. Okay, so the next thing that I didn't introduce very well before, but we will be already familiar with this, is that we want to understand what would be, omega g of a Gaussian state phi phi. And that would be exactly this. And I didn't define Gaussian states, but what I will be betting on is that you will be comfortable with just assuming that this is just a pure state in Hilbert space. And the Hilbert space will be C to power 2 to power L. And basically, there will be some Majorana operators defined here. So Mj, Mk will be 2 delta Jk. Okay, and this we could take as the definition of a Gaussian state. Actually, this is something that Bravyi is doing in one of the papers. So there he's just starting with this as definition of a Gaussian state. So basically taking this form as the definition of the Gaussian state. So a couple of words about what this thing here is doing. The first thing that we can verify is that actually when I have this in the notation previously as omega g of some pure state phi, then actually I can compute already the trace. So how does it work? Identity will be mapped into the identity symbol in the Grassmann algebra. So then I can compute the trace of phi. For now, you don't need to trust that it's a pure state. You could just say it's just the operator. So for example, you could also say that omega minus 1 applied to this a of theta. You could just say that this will be phi. Yeah, so you just denote it like this, but it's actually a state. You can check it. This trace we can compute as the integral against p and q we had, then the kernel, which is doing the contraction, and then omega p of identity, and omega q of the state phi. Yeah, and I think if we, so I'm not sure if I should be computing it now, but the idea would be that one of the integrations is again giving us a Gaussian integration, and the other integration will be picking out only this 2 to minus n. So basically we should get somewhere, we should get a factor of 2 to minus n, 2 to minus n, and that way we will get the identity or the unit normalization. So all this discussion is to say that basically this you want to interpret as normalization, and you could also try to compute this normalization in the Grassmann formula. So without computing this in Hilbert space, we have enough formulas from previous papers by Bravyi to compute this trace. And in principle, what we should expect is that there will be this 2 to power n somewhere. And I think this 2 to power n will appear from the Pfaffian of the matrix M somewhere, but I'm not exactly sure. So that's more or less where it should be going. Okay, the other stuff is, this is something that we were actually proving in a little bit more detail. So so I think I will not be commenting much on this. Then there's the integral that we were discussing also in relation to Shor's complement last time. So basically this is a generating function, a little bit like a generating function. So what happens here is that we fix one integration variable eta. This is the variable of the quadratic form. And then there's some added Grassmann number theta. And this is what this integral gives us. So basically it's again a Gaussian form in Grassmann's, but now in the new variable theta. This eta vanished completely, but it additionally gave a Pfaffian of matrix M, which was sitting here. So this is coming from that. It's a little bit like completing the square. And when you want to complete the square properly, then you get this m-1, and that's important because we assume then that m is at least in GL of 2n. Yeah, so this invertibility here is quite crucial for those formulas, but this will be useful throughout. Then we were already defining those bilinear forms. I think that was 1 or 2 weeks ago. And I was saying that this is maybe more general than you need it to be. But in this paper, this is extensively used. And I kind of forgot why I was putting it in so much detail. But in this paper, it's really crucial, and that's basically why it was appearing. Okay, let me zoom in like this maybe. Okay, so we continue further. This is just a recap of, just to see that we saw some of those things already. So once we have this gamma, then we can, for example, compute those traces, and that's a trace that I was computing for a long time. And this, actually reading this appendix has motivated me to study some other stuff. So for example, here they only need the traces of products, but I was giving the general formula already of mu m nu, and we saw that this was m new binary addition with nu, and then you need to additionally factor in this gamma function of mu nu. Yeah, so I will remove this because, so just to say that we saw this without the trace, and you just in this notation would add c plus y here, and it would probably work. And this 2 to power n is just a trace of identity. And in some way, this is also the Hilbert-Schmidt orthonormality, because what we also saw is that the trace of m of mu dagger m of nu was easier to compute, and that's just the Hilbert-Schmidt scalar product. And if we would normalize it to, yeah, so this is 2 to power n delta mu nu. So we saw something like this. And yeah, so just to say that this should be familiar. The next thing is what we were actually computing explicitly. I think I was kind of confused about the orderings. You should understand what this notation means. I think for this paper, this still means what we were writing like this. And this factor here was coming from integrating G to L, G, P to L, and so on, ordering like this. So reshuffling the integrals and adding a swap, a sign flip every time you swap integrals, or when you swap the order of integration, you flip the sign. That's this factor coming out of this. And this is for connecting them together in some way. So those rearrangements were important, and we saw this already. So that's part of the recap. And here we explain the notation that this is just what I saw. So first against G and then against B. So then if we expand in the Hilbert-Schmidt basis, we see the trace formula that we already saw. Okay. So this is just the formalism we were covering. And now we will see how this comes into action. So now we should slow down a little bit. So A and B. So in this formula, A and B will be two projectors onto some Gaussian states. So those Gaussian states are the special states with a Gaussian characteristic function. So basically those A and B operators will be mapping into such a Grassmann varied quadratic form. And I didn't say one thing that is maybe a good side remark. In some of the papers cited in this paper, you will find previous papers by Bravyi where this is just a covariance matrix in the state. So you just take mx, my, commutator of the stuff I have, phi, phi, and this defines for you this MXY matrix. Okay, so so this is not stated in this paper, but there's much more behind it. I didn't have time to develop this carefully, but I really want to show the paper today. So basically, if you have a state, you can compute this observable. This I here is to make sure that it's an observable, because MXMY dagger is not Hermitian, because it's MY MX dagger dagger. They are self-adjoint, so this is MY MX, and then they are anti-commuting, and this is minus MX MY. So anytime you get something anti-Hermitian, then you add an I, and you make it into an observable. So this I is actually coming from this kind of stuff here. Okay, so that was just a recap, because we will be now working a lot with Gaussian states. So
can you comment on what property should M have that you see immediately that the state is pure? Maybe you mentioned it already.
yeah, M should be, whoops, what happened here? Did I mess up the colors for you? Or? So M should be orthogonal for the state to be pure. And I was not showing this. Why is this blue? Was it blue for you now?
It was blue, now it's a bit gray.
Yeah, sorry about that. This is something going on in Chrome. Wait, maybe I can. Okay, I'm reloading it. Sorry about this. So that's actually why I'm kind of rushing through everything. Because I wanted to come to this paper, to this appendix, and I feel like we have almost just enough to discuss those crucial formulas that we wanted to get to. Of course, those Gaussian states have a lot of properties. And one way to prove this is that basically you start having some representations of Gaussian operations, and then you can try to put this into the normal form. I was mentioning the normal form already, but I didn't work much in Hilbert space with unitaries. So okay. One comment is, if I have MXY defined as I over 2 expectation values in some pure state of MX MY phi. So this is an observable, and now I don't have I anymore, and X is maybe smaller, strictly smaller than Y, because when X is equals to Y, it's just an identity, so it's just normalization. So that's easy. So basically, taking the commutator is actually removing the identity, and makes the entire quadratic form much nicer. So we have this one. And now, because we know that mx squared is identity, then we can use submultiplicativity of norms, and operator norm is actually multiplicative. So we find that m has norm equals to 1. Yeah, that's a quick trick to see that. So by Cauchy-Schwarz, we have that m as entries should be smaller or equal than 1, but it's actually stronger if you start diagonalizing it and putting it into the normal form that I was mentioning, that I didn't develop. If we will make another thematic session for Gaussian operations, then we will have time to develop this. But M can be put into a form by an orthogonal transformation that we already saw. 0 lambda k minus lambda k 0, and then that's also in some of previous papers by Bravyi, this lambda k has to be plus minus 1. And if it's actually attaining it, so if it's equal to 1, then it's a pure state. That's the condition for purity. So there's a simple relation, namely 0 m smaller or equal than 1. And those are the physical states. Those are also density matrices. And if mt is equals to 1, then we have a pure state. So this is basically positivity. Trace normalization is easy, it's always like this. And this is purity. Yeah, and it's coming from this normal decomposition. And we kind of see that we cannot be larger than 1. Purity is when you go to the bound, and positivity is sitting inside of this interval. That's what we need here. Okay, so those are the conditions, which means, Lucas, you're right asking about this. We will always have in this paper MT is equals to identity. That's something we will always have. So now we continue to those pure states that were appearing. Okay, so we take two pure Gaussian states, which means that it will have M0 and M1 as this covariance matrix, which means in the Grassmann representation, they will be two Gaussian exponentials. And then you can use this trace here to compute the fidelity between those two pure states using the Grassmann formalism. And we have this very nice formula here that we were kind of deriving. We were really motivating in one session why this is the right formula. You see that it's a very nice nonlinear function of those two covariance matrices. I will be calling them covariance matrices today, but basically those kernels of the Grassmann varied Gaussian function. That's the interpretation of the fidelity between those two states. And what today we want to look at is much more complicated expressions, basically triple product formulas. And if we will be reading through it, we will compute something much more complicated. So if we take the Gaussian form, then we can compute its expansion. So if I have x of minus I have in this paper theta capital T m theta, then we can expand this in our ordered monomials, and what we will get is e minus half to power mu half, I think, and then theta of mu, and the coefficient will be Pfaffian of m, matrix M restricted to rows and columns indicated by the binary string mu. Okay, and this is called Wick's theorem. And basically what we want to see is the generalization of Wick's theorem. So if I just have phi and I compute m of mu phi, then this will be minus e to power mu divided by 2. And let me put an eraser. Okay. For a Gaussian state, this will be defined as Pfaffian of the matrix M restricted to rows and columns where mu is equals to 1. So it's taking Pfaffians of submatrices, and that's called Wick's theorem. And it could be an exercise that we could do, but I don't want to go to those details. I want to give an overview of the entire appendix just to see where we are, and then we can get some feedback and maybe go through the details. But this is just Wick's theorem. And now the question is, what happens if I take phi 0, again, m of mu, but then I don't repeat the state and I take phi 1. Yeah. And this is what they will compute today. And this will be some Pfaffian of I, some delta of mu, where mu is x in this paper. Okay, so the only difference is what happens if you have two different Gaussian states and they are possibly non-equal. If they are equal, then this is the classic result, which they will be referring to Wick's theorem, and this they call generalized Wick's theorem. So this is where we want to go to. Okay, and
so just a comment. Whenever you have that, then of course you actually also have a dependence on the relative complex phase, no?
Yes, and that's something that I will be roughly skipping because that's, for example, why they will be adding this. So they will be checking the parity, and then first of all, when you read the paper, Grassmann formalism for now, and suddenly what's going on next, right? So, for example, they have this hyperplane condition here, and this hyperplane condition is so that you will be just enough traceless, yeah. And then they are adding this parity here to remove certain things and so on. But the motivation is that if I had this generalized Wick's theorem here, phi 0 m of x or c of x, so m of mu in the previous notation, phi 1, then they want to be computing this as phi 0 being the first operator, then maybe m of mu second operator, and phi 1 the last operator. So each of them you can linearly expand in the Majorana basis. This will be easy, but this will have some coefficients, but you then linearly expand, and you will be going towards formulas like this. Okay, so they don't explain why they are going to it here. I mean, they do it probably in the paper, but this is just showing the computations, and that's our focus here. So this is basically for phi 0. This is for the observable, and this is for phi 1. And then you need this parity here. And when I will scroll down, you will see that this phase that Lucas, you were asking about, it will be appearing. So they did it carefully. Okay. So the next thing that appears, so this is more or less similar to how I was discussing the previous trace formula. So first you compute on the basis, and you compute which kind of coefficients you should get. The expansion coefficient, so for example, some A mu, B mu, you can add by hand, and you can sum over them outside. So then you get the operators in. So on the basis, we have this kind of triple product formula. And this trace is 0 if we don't have this hyperplane condition. And then this is very similar to what we were already doing once. It's just a generalization to free operators. So we have three Grassmann variables, each variable for each operator. And then we see, okay, this is very similar to this stuff here. And you see that those bilinear forms are appearing here. And my question is whether those bilinear forms are somehow related to those symplectic forms. So that was one discussion that we were having, because for stabilizers, those would be maybe some symplectic forms. And for the first time, we see a more complicated expression here with those gammas. This is basically one is coming from multiplying with this, another one is multiplying with that, and then yeah, that's more or less that. I don't want to be doing the derivation today because we still have two pages to go. Okay, but once we have this, then it shows that Grassmann integration like this can compute this triple trace upstairs. Yeah. So now what we can do is basically you can in this notation you can replace not like this. Sorry about this. We could replace in this notation here A by theta, B eta, and C of mu. So those would be those characteristic functions. I like better the notation of taking the operator and mapping it to, for example, G omega P of B omega Q of C. So this formula here is already what it achieves. Yeah. So we can integrate, instead of having this, we could put in those omegas like I was writing, and this is the contraction kernel that is implementing the correct multiplication and doing the trace. And doing this together will give us the product. Okay, so this is what they will be doing actually here, I see now. So I was jumping ahead. So now we take any three even operators. We take three operators like this, and those are their generating functions. Okay, so here we are calling it generating functions, fine. Okay, too fast. This is already the result, but it's coming fast. Okay, and exactly. So by linearity, if you sum up over the bases, then we get this triple trace formula here. And the parity is really taking the face in the end. So, okay, let me blur out one part just so that, okay. So if we look at this, this is the thing that I was discussing just now. I have three operators plus the parity, and this can be done by taking those generating functions, as they call them here, and integrating it with this contraction kernel, and this gives us a trace over three different operators. So the next thing is to say that those ABC are those projectors onto the Gaussian states phi 0, phi 1, phi 2. Yeah. And phi 0 will be playing the role of a reference phase. And phi 1 and phi 2 are actually the Gaussian states of interest. That's the notation in this paper, as far as I remember correctly. So, okay, so let's continue reading. The notation will be, there will be three different covariance matrices. This M0 could be chosen to be the vacuum or some reference state. So this will be a fixed matrix M that will be used for this phase reference. And then they say, okay, any Gaussian state has a fixed parity that is P on phi. I guess as a catch, will give us phi alpha plus minus 1. And yeah, here they just explain something about the parity and so on, which is simplifying the calculation, but I'm skipping the calculation. So yeah, so we are putting everything in, and basically, so this is something that they need, but later they will still generalize this a little bit more. But basically, it's like a triple chain of fidelities like this. And this is something they need as a normalization, okay? I'm wondering if I should maybe show the equation 24, but let's just continue with the calculations and let's just see what's going on. So yeah, we are almost at the generalized Wick's theorem. It's just that they needed to construct this new matrix here. Okay. So let me show equation 24 and 25. Sorry, maybe I should have shown the main text. But the paper is very long and the appendix is condensed. So I wanted to show the calculation. I thought it would be easier because the paper is quite massive. There's a lot of things computed here. Okay. There's some notation that would have been helpful. Okay. Sorry, I need to refresh. Okay, so back to equation 24, verse 24. So this we know, that's something we computed. This we just computed, okay? This is just the Gaussian representation. We already had it there on almost written there. And then those things can be simplified. Okay, that's some discussion here. But I want to show something more relevant where we want to arrive at this. So this is what I was writing. Phi1 and Phi2 are two Gaussian states, and you don't know what they are, but you know the covariance matrix. C of x is an observable, and then they say this is equal to the fidelity between those two Gaussian states, okay? And then multiplied by Pfaffian of delta x, yeah? And that's basically all that we have in the main text. So I kind of skipped it. But the point is that they show it as this kind of formula. And we will be using this phi0 because if you do it like this, then phi1 and phi2, it's basically a phase can be removed somewhere here. So so I think somewhere they have a nice discussion why they need to also add a reference projection. Maybe it's somewhere here, but yeah. Anyway, yes. So we need to understand what's the. So this kind of expression could be a complex amplitude in general. So what they say is to make it not arbitrary in terms of the angle in front of the entire state, they will be saying, okay, reference to phi0 and phi2 also reference to phi0. And then this expression here is what we were computing. So once we have this, you have a way of working with superpositions of Gaussian states. So that's what this paper is doing. It shows that ground states of quantum impurity models can be expressed as polynomial superpositions of Gaussian states. That's the next kind of 40 pages in the main text. So basically here they talk about coherent superpositions. When we are working with coherent superpositions, then we have the phase that Lucas was asking about. When we want to ask about the phase, we need to reference it to some particular, I guess it's like a gauge choice. Phi0 gives you a gauge choice, maybe. But anyway, so that's why this is appearing here. So you cannot just take it easily like this, because the way they compute this is by going into the projector representation. And when we will be working with the projector, so let me write down the projector. So in principle, I can compute this up to some EI alpha trace of the projector phi1, phi1, observable Cx here, and then multiplied by phi2, and close the trace. But because we are doubling this, then if phi1 was carrying some phase EI alpha 1, then we will be missing this because we are forming the projector. right? So this is good because we can compute it in using the Grassmann formalism. In Hilbert space, it's difficult to compute this, but it creates this difficulty that if there was some special phase, complex phase in front of phi 1, then we might be missing it. And I think what they explain here, either it's explained here or in the appendix, is that the way to get this phase back is to ask what is your fidelity to phi 0, to some fixed reference state that you never change during the computations. So that's why those two are appearing, and we are almost here to compute this using the projectors. So we are almost there to compute this parity ABC. And without those two states, this would be missing the complex phase. So you add this and this, that way we get the complex phase because there's something more going on here, and that's why we are happy, okay? So that's the main text, and they are saying, okay, we are trying to prove, I think they are saying we are trying to prove this formula, 28. And the actual formula of interest is this formula somehow. All right. Okay, so that's a lot of talking and maybe jumping ahead. Sorry if this was jumping ahead too quickly, but okay, we saw the notation of this paper. It's mostly things that we are familiar by now. And we are almost there to compute this complicated formula. So, okay. When A, B, C are projectors, we get this expression here. And this is equation 24 from the main text. Okay, so let me see about equation 24. So this is this chain of fidelities here. All of them together are this fixed phase here. So now equation 25, we go back to 183. So we get this. And you don't integrate everything over mu here. That's what they say. 178 is just this thing that I was explaining with m to power -1. I think, yeah, I was right. So it's a partial Gaussian integral. There's still this variable here. So I remember that in the derivation it's a little bit hard to follow, but I just want to show that with the techniques that we already know, we can kind of follow at least what's going on. The derivation is just more complex than, yeah, yeah, there's a lot of stuff going on, and in 1 hour showing the whole thing, it's I think stretching it, so I will be just very brief. Okay. One thing that will be going on is that this that they basically iterate the integrals and basically build them up one by one. So, for example, here taking a partial integral, which already means that we removed c of mu. Yeah. So they didn't write it down here, but here we had the complete integral. Then we are using 178. Okay, it jumped. 178 was this partial integral, and step by step we are moving forward. And now we have, for example, this m2, but the inversion of m2 is actually minus m2. So we get a minus sign because they are pure states. Yeah. So already one thing that is maybe tricky is that this is minus m2. So for example, here we would have to notice the phases, and I don't want to go into those details. But basically what's going on is that B, if I remember correctly, then M2 was here, and now we would need to understand why this is eta minus theta. This makes everything a bit more complicated, but it's always iterating this like this, because this is again in the standard form. So now this delta is the Schur complement. We saw Schur complements before, because now we see that for the variable that will remain, so the last one is theta, actually this eta, theta, the mixed product. So for example, like this, there's M2. And basically for Schur's complement, we would have maybe M1, M2, and then some coupling by B. So this should be viewed as Schur complement, and I think this was 1 or 2 weeks ago. So we were discussing this in more detail. And for example, if I take theta here and I take theta here, then my quadratic form is M2. But the coupling between theta and eta is the identity, but also sometimes I times M2. So this is the B matrix in Schur's complement notation. Yeah. So this is where it arrives. So it's kind of painful, but they just went through the calculation and they get those formulas, and that's how they were able to prove all the results. Yeah. So once you have this, it's just a standard Gaussian integral, and now it's the complete integral. So you put a smiley face, and you just have this one. Yeah. So yeah. So taking into account this stuff, you can simplify this, and things are appearing downstairs. And basically, for example, here you have twice the same stuff. So M2 like this. So 2n goes into 4n, and you're almost done here. Yeah. And now a couple of comments. If you would be doing this phase insensitive, then you would only have this delta, M2, M2, M1, M2. Okay. But because we have a reference phase, yeah, so this is doing the reference phase, which means that this way, this computation here will be in some way sensitive to amplitudes, and will give you the complex amplitudes. So this is the reference phase. This depends only on M1 and M2. Okay, so this is kind of how this information about those states here is encoded. Okay, so once they have this, they go one step further. Because now they say, okay, let's actually prove the Wick's theorem. Okay, so before I go there, I mean, this one page is basically how those Gaussian integrals are done. If this is 3 different integrals, there needs to be like 3 different steps, and that's what I was discussing. Yeah, that's all. And each time you do a step, you will get a more complicated matrix, and that's what's happening here. In the end, they are quite natural, as much as they can be. After all those simplifications, I think this is actually pretty good. So I'm not discussing those simplifications because that's maybe not the most important thing. Just one thing that will happen to prove the generalized Wick's theorem will be that, okay, so here's some discussion, but this is the crucial bit. You construct a new operator where you apply this Majorana operator to phi2. And once you have this, you kind of see, okay, I express this as Majorana operators and multiply with Cx. The expansion of this in terms of Majorana operators is basically going backwards. So, okay. So omega g of phi, we said that this is 2 to minus n x minus I half GT mg. So now if I apply omega minus 1 to this, I will actually get phi phi. So I apply omega minus 1. So I get phi phi. But this gives me the expansion in Majoranas. So there's this thing going on in the background, where we have to take Pfaffian of M restricted to rows and columns indicated by mu, and then M of mu. So without saying this, we did this expansion, yeah? Because the definition of the Gaussian state here is as a Gaussian expression in Grassmann numbers. So when you go back, you kind of realize that if you write this as the sum over all G mu's, what are the coefficients here? So phi mu, so to speak. And those phi mu's, if you do the computations, it's the Pfaffians of restricted matrices here. So that's in some way Wick's theorem or whatever. But this is this Pfaffian of minus I here. So minus I here, I just missed it. Yeah, so that's the expression. But now to multiply this one in, you just do this and insert the gamma here. That's all that is happening. Yeah. So we will be going for the PABC form, but C is actually in some way twisted projector because it's dressed by the C of X here. Okay, so it follows that C has the generating function by definition, and using the computations that were maybe not spelled out here, that's what's happening here. Yeah, and now because of this, things are a little bit more complicated. So we will get more complicated generating functions, but we are almost there. So too much scrolling. Wait. Okay. So it follows that it has this. So here is a vector of Grassmann variables. It's just this. Construct a linear map acting on Grassmann monomials such that if you apply this to a string, you will apply this and shift by this index X. Yeah. So this is a Grassmann representation of multiplying in that vector. And there is formally a more formally complete way of writing it, but anyway, C mu is just applying this map phi X to this stuff here, and then they do all those computations here and represent this. Basically, this is a map, and maps. I was mentioning this motivation of Grassmann integrals as basically integral operators. So if this is a map and I apply this to some element of the Grassmann algebra that I'm working with, I could try to represent this map as an integral operator. So if I apply my integral operator to f, I will have some new function g, and I obtain that new function g. It will be going into mu prime prime, if I'm not mistaken. No. Because okay, so that's like it's like a super operator in some way. But anyway, there is some dummy variable that we are integrating against here, and it will be completely removed. And this is basically a Grassmann variate integral operator. Yeah. So without explaining much how you find it, it's given to you, and it's a little bit like again a contraction kernel. Yeah. So this is an explicit representation of phi X as a Grassmann integral. So there will be one more additional Grassmann integral going on here. Yeah. So now basically the fun begins, because this is exactly what we wanted to compute. Yeah. And then we arrive at this. So formally, this is an expression that is valid for any state. Yeah. So basically, I could take those to phi 1 to be B. B is phi 2. Sorry, phi 1 is B, and so on and so on. Yeah. So phi 0 could be any state, strictly speaking here, and those two are contracted together. Yeah. So this is general expressions, and they are in boxes because they are valid for any state. It's just for any state, you might not know what is this generating function here, or the characteristic function if you want, and so on. Yeah. So the only case when we can do it nicely is using again Gaussian integrals, where basically A, B, and C are Gaussian operators. So A, B, and C, if they are Gaussian operators, then we are getting Gaussian stuff here. And basically, this is this trace is a functional, and this is a way of writing it again as an integral operator. And that's the kernel for this trace and triple product here. Okay, so basically, once this becomes a Gaussian density function, then this is A, this is B, and this is in some way C. It's just that C of mu has an additional theta integral. I don't want to discuss this too quickly, but that's what we just saw. And that's the final form. So we pick out all of those things. So theta to theta is M0, eta to eta is M1. Then this stuff is a little bit more complicated because of this deselecting which kind of observable we have. So they just introduce those things. And basically this becomes one big, Gaussian integral. So we have a Pfaffian of one big matrix, yeah? And that's basically the end result. So that's this generalized Wick's theorem, which means that we have this trace PABC, which is the sequence of fidelities for the reference phase and the actual expression here, which they arrive at with this big matrix. And that's all that you need. Basically, what you need to know is that C of x is encoded into dx and jx. So what is dx? Dx is a diagonal matrix of size 2n such that dx is 1 minus the string x. It's basically putting your indicator string of the observable onto the diagonal with a flip. Yeah. And jx is a matrix such that it's 1 if the position in the if is non-zero x, and otherwise it's 0. Yeah. So those are simple matrices that are indicating where you are multiplying in the matrix operators, the observables, so to speak. Yeah, that's all that is happening here. So that's why there are 4 blocks, because we have one state for referencing, another state on the left, then observable dx, and you need to multiply with the observable. So this is implemented here. And then the final state here, which is just by this implementation of, yeah. It's super complicated. If you look at the end result, 187, I actually stopped working with this paper because I was like, this is making me dizzy, those matrices. And it's kind of maybe that's the hallmark in some way to me of what you can do in the Grassmann formalism. Because if you work backwards from this formula, to guess this formula, I think you have to be quite brilliant. You know, Ramanujan maybe would come up with this, or some algebraic genius. Because, you know, it's like, how do you get this? I mean, maybe at some point you guess that there should be some short complements and stuff like this. Those identities are always like the multiplication kernels, so that's how it works. But then to find the correct dx and jx, I mean, this is not so easy. Then jx and dx are on 2 different sides here, and so on and so on. So this is not obvious. And then it's a highly nonlinear function of all of this stuff, because Pfaffian is nonlinear of this block matrix here. And that's basically this Wick's theorem here. Yeah. So to me, this is the power of this Gaussian formalism, because you could say I try to compute this stuff just pedestrian way in Hilbert space. I forget about Grassmann's. That's kind of the formula that you will need to arrive at. Yeah. So no way you can do it directly, I think. Which is sort of my last comment for today, I think. Yeah. So that was very quickly paced, but it's just showing that we had enough to be discussing this formula. It's monstrous, but it's monstrous because there's like monstrously many things coming in. You need to take care of phases. This is already adding like 2 fidelities. Then you have two different states. Each of them has a covariance matrix M1, M2. M0 can be fixed in the entire calculation, and you have an observable. You need to encode this. And then because you reduce everything to Gaussian integrals, there will be a Pfaffian of something. But this something has to be very big because there were many ingredients. Because you need to somehow connect the ingredients, you need the identities on the side. Yeah. So we were kind of seeing for the fidelities how. So fidelity between two Gaussian states was just this block. Yeah. So for example, this is how Pfaffian of such a block is the fidelity between phi0 and M1. But the product of all those fidelities here is like this more complicated matrix. That's the meaning of this formula. And basically, that's why I didn't even try to prove this. I was kind of sketching proofs of other things, but here I'm just going through the notes. If we scroll through it, it's 58. And I mean, this is not one page of notation, second page of notation. For us, it was 2 or 3 weeks. Then we understood those things this we were computing. And then 57, 58 is basically the computations. But it's really dense computation, so that's why it was so quick today. Okay, so if we will ever need it, we can discuss the proofs. But basically, once you understand the proofs, you also understand how to work with the formulas, and that's what all that you ever need. I think you cannot make it much nicer, the proofs. So there's not much to get there, and you can only be happy that they derived this because it's quite a powerful formula. Okay, so do you want to give me any feedback or comments on the recording, or should I finish the recording session now and we just move on to the discussion? So, okay, I will finish it here. Wait, no. Here. No.